We're going to do some examples for row space and column space. So our first example has a matrix E, and we're told to find a basis for its row space and for its column space. So start with the row space. The row space is just a set of all linear combinations of the rows. So we just have to eliminate redundant vectors from the rows. And we can eliminate the bottom row because it is just full of zeros. And we can tell that the top three rows are linearly independent because there's a 1 here where there's zeros here. We have a 1 here where there's zeros on top and bottom. We have a 1 here where there are zeros here. So since these are linearly independent, we can write the basis as 0, 1, 0, 2, 0, 0, 0, 1, 3, 0, and 0, 0, 0, 0, 1. Now we look at the column space. And the column space is just a set of linearly independent vectors, or a set of linear combinations of the columns. So we can eliminate this column because it's just zeros. And then by the same procedure as before, we see that we have 1 here and zeros here. So that is going to be linearly independent from this one because there's a 1 there and zeros there. And we know this will be linearly independent because there's 1s and zeros. But this column, we'll call it B3, is just 2 times B1 plus 3 times B2. So it's linearly dependent on the others. So the basis for the column space will be 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. Okay, so now moving on to our next example, we have a matrix F that equals 1, 1, 1, 1, 2, 2, 2, 2, 1, 2, 3, 4, and 1, 3, 5, 7. And we're asked to find the basis for a column space and the basis for the row space. So we'll start with the row space again. The way we can do this more formally is by putting this in reduced row echelon form. So we can take R2, subtract 2 of R1 from it. So that row becomes 0. Then we can take R3 and subtract R1 from it. We get 0, 1, 2, 3. Then we can take R4 and subtract R1 from it. That gives us 0, 2, 3, that gives you 0, 2, 4, 6. And we can swap R2 and R3. Giving us 0, 1, 2, 3. And we'll actually swap R3 and R4 as well. Because we know that the rows full of zeros need to go on the bottom. Then we can take R2, subtract R3 and subtract 2 of R2 from it. Okay, then we can just take R1, subtract R2. We get 1, 0, negative 1, -2, and then 0, 1, 2, 3, and then 2 rows of zeros. And so, if you look at this, column space is just, the bases can be formed by whichever, the row space, the bases can be formed by whichever rows have leading ones, so the first and second one. So our basis for the row space is 1, 0, -1, -2, and 0, 1, 2, 3. And the column space, its bases can be formed by whichever columns contain a leading one. So this one and this one. We have to be careful not to use these columns themselves like we did for the row space. We actually have to go back to the original matrix and look at those columns. So we actually use this column and this one. So 1, 2, 1, 1, and 1, 2, 2, 3. So while the row basis, the basis for the row space is not affected by these elementary operations, the column space basis is affected.